Practice. She said, "Dude, I have another gift for you. You're going to use this one here in a second. I'm going to give this to you now, and we're going to label it out. What this is are the metric prefixes. These things will become near and dear to your heart. If there's anything I can say to you is, as I have said before, in this class, everything comes together. You get to learn my two most famous sayings today. These are ones that you're going to hear continually throughout this class. And if you had me for physics, you would hear it in there as well. Number one, once you learn it, do not forget it. Because of number two, all is fair game. What I'm saying in that, once I teach you it, it is fair game for me to ask you it. It does not matter. We could be on week 16 in this class. I can ask you something from week 1. Because in chemistry, everything comes back together. We get to one central subject and it's like a puzzle. It just comes together. Ever so sweet and nicely. Okay? With this, I want to point this out to you. On your metric prefixes, I've given you more on here than what I will require you to know. But on this chart, there are plenty of them you're going to have to know. So right here at the top, you see peta. I do not want you to know anything greater than peta, so you can make a mark there. I gave those to you so that you know those others do exist, but the truth of it is, I have never used those prefixes ever in my life, and if I made it all the way through college without using them, I'm not going to require you to, especially because as smart as y'all are, you're going to have these things down pat, and if you can memorize the ones I'm going to give you, what's adding 6 more? So, the other one we're going to go to is down at the bottom. It's femto. Okay? I will openly look at you and tell you I've given this to you for you to study, for you to learn them, for you to apply them. I will also look at you and tell you, as I always get this fateful question in here, Gage, I'll go on and answer your question. No, you cannot use this on a quiz. That's not going to happen. You are to know the symbols. So as you can see there in that column with the symbols, micro is actually different, by the way. I'll show you micro here in a little bit. The one that I like to go by, I don't worry so much about this multiplier traditional notation there with the really big numbers. I'll have a method that I'm going to teach you today. I don't know if I'm the only person that's came up with this, but I figured this out during student teaching and I've been working for years to perfect it. So we've gotten pretty close. I'm going to teach you my system to doing these metric conversions. The reason I'm going to do that is because your calculator does not care how you give it to it. It's just going to do the math. So if the calculator don't care and we're just going to be punching this stuff in, I want to make this as simple, fast, and quick and easy for you as possible. So what we care about is over here at these exponential values. And those negatives absolutely are very, very important to us. Then that description, that's just extra information there for you. Is there any questions? Anything? Fantastic. Let's get started. If you've not known me, my name is Mr. Hall. I'm excited for you to be in here. You are my only chemistry class this year. We're going to have a great, fantastic, wonderful time. There may be some tears, but it's okay. It's all right. We're going to make it through. If you have questions, ask. Help you as much as I can. Today we're going to start on something that is probably one of the most important concepts and ideas found within science, overall, hands down, so important. If there's anything you're going to learn from my class, you're going to learn the importance of this. Today we're going to talk about the International System of Units. Within this International System of Units has a weird abbreviation to it. I got to give it to you so that you'll get it. Within this, this International System of Units, you know how science is? We don't make a lot of sense sometimes. You look and go, why did they do that? That's just dumb. I totally understand. This is the abbreviation for the International System of Units. The SI system. I have no idea why we chose that for it, but that's what we chose it for. Within the International System of Units, this is where the whole thing comes from. Is the whole problem of it is whenever you look at it, that's interesting. Whenever you look at it, would you see a big problem? Bless you. If somebody over in France does an experiment and they get data from it and they have different units than what America uses. So then I'm in the lab, I repeat the same procedure and everything they did, but I have different units, so we don't come up with the same exact stuff. Do you see that as a big problem?
Yes.
Yes. It's a huge problem. So this is what happened. You'll get to learn about it here in a little bit, but what really took place is during the French Revolution, some things have changed, and it gave science the ability to work some stuff in, to change the unit systems that are being used around the world. So literally what they created was this International System of Units. What's the purpose of the International System of Units? So what the purpose? Is to keep everyone on the same track, on the same path. It's to keep all of our units the same. So nothing, even if they're dealing with a different language, the units are still the same. They're identified as the same. Therefore, the data they get from their experiment will be the same data I get from the experiment. It'll be the same. So the purpose keeps all us people, all us, not all of, all us people in the world of science on the same path in terms of units. So are there any questions there? So within this, I'm going to tell you and I'm going to give them to you. Now I want you to get familiar with units. I don't want you to have a heart attack with them. I will look at you and tell you there is 7 defined base units within the International System of Units. Every unit outside of that has these units involved in it and used, but they're just representations of scientific properties within our world. So this is what we're going to look at. We're going to be looking at the base quantity. We're going to be looking at the unit. and we'll be looking at a symbol. The symbol is just so important because scientists like shorthand stuff. They do not want to have to come in here and keep writing the unit's name out, so we use abbreviations, which are those symbols. You've seen some before. It's not that big of a problem for you. Like a perfect example. We'll start with ones you're used to. Let's do it in black. So the first one, the base quantity. So the quantity of this measurement is length. You've all seen, heard of this unit before. This one should not throw you off. The base unit for length in the International System of Units is the meter. Its symbol is just a lowercase m. I'm going to stress this out to you now before anything. You guys still got your metric prefixes handy? Go down to the one that says milli. You see milli there? It's 10 to the negative 3. What is the symbol for milli?
M.
It's a lowercase m. This also is a lowercase m. Here's the difference. That's a prefix. You should have learned in English prefix, pre, before. This can stand by itself. If there's anything I'll look at you, I will openly admit to you, when you're taking a quiz of mine, yes, there's tricks on it. I am trying to trick you. I am openly admitting that to you right now. This right here is one of my big tricks. I will literally throw a unit to you that is just M. If you just see M by itself, what is it?
Meter.
Meter. It's not milli. Do not look and say, those are millimeters. No. Millimeters is M. Prefix. Before. Base unit. By itself, it can stand. The prefixes cannot stand by themselves. Got it? Just got like everyone just like looking at me, not really talking with me. I promise you, I'm not going to smack you in the face with a 2x4 today, okay? It's going to come later on. Later on. It's not that big of a deal. Promise you, this is about as straightforward as it gets. So that's length. Alright? Now we're going to move out of length. We're going to go to another one you've probably heard of before. The second one. And so you guys know I try to use different color markers. If you are colorblind, I apologize. I'm so sorry to hear that. If you tell me, I will pick with you and have fun with it. It's funny, but I'll help you. I use different color markers so that you can like defer what I'm talking about. So what's in black is applying for length. What's going to be in green is applying for mass. So the base quantity of mass. Remember me telling you that scientists, you look and you say, why'd you do that? This is one of those moments that we sit back and we go, why did you do that? The unit for the International System of Units for mass is the kilogram. This is one of those moments that I, at least, am looking back and say, why did we do that? Why? Just why? That's so stupid. Because, look on your prefix chart. 510 to the third. What is that prefix?
Kilo.
Kilo. This has a prefix already in it. This is the symbol for it. It is kg. here's the thing. It has a prefix already with it. So if we were just talking grams, we were looking for grams, what would the symbol for grams be?
G.
Just G. This is a good point that I like to stick out something to you. Knowing what the base unit is. If you know what the base unit is, it helps out a whole lot. G is the base unit. The K is a prefix. But anyway, these fancy scientist people back during the French Revolution looked and said, well, hallelujah, let's just make mass kilograms for whatever reason. Don't know why we just went with grams. Next one we got, number 3. You've heard of this one before as well. Number 3 is time. The base unit for time, as you can probably guess, is second. The abbreviation for second is an S. Just a lowercase s. Here's why I like doing and going through this first with you all, is to show you units that you've never seen before that exist, that you need to get yourself. Don't freak out that you hadn't seen the unit before. This is a trick of mine that I will use. I will openly admit to you right now, I literally use units you've never seen before with one intent. For you to look and go, oh my sweet God, what is that? I don't know what that is. And you totally forget you're just looking for the prefixes. Okay, which comes into play here in a second. Number 4. This is the International System of Unit for an electric current. Does anybody know what this one is?
Watt.
It's a good guess though. It's ampere, or as we more popularly know, amps. The abbreviation for ampere is a capital A. Yes, it matters. Capital letters, lowercase letters, they matter. Number 5 is temperature. We all have dealt a whole bunch with temperatures lately. Every time I come into the school, Mr. Reddy's like, beep. And every time you walk into school now, there's a big fancy camera looking at you, saying, how hot are you today? You good. Not at 100, you're fine. Number 5, we deal with temperature. You guys just aren't feeling it today, are you? Or y'all just like really intimidated and you think right now I'm about to just like blow out some mathematical expression that's going to flip everybody out and you're going to feel like you're going to die in this class. That comes later. Okay, so we're going to talk about temperature. And it's not like what you normally associate with it. This one is Kelvin. Very close to Kevin, but there's an L, so Kelvin. The abbreviation, the symbol for Kelvin is a capital K. Okay? I'm gonna do number 6 in the color brown. That sucks. We are not doing number 6 in the color brown. We're going to do it in whatever color this is. Number 6. You guys will be learning about this later on.
Are you okay?
I'm good.
I'm awake now.
Hang on too. I rolled my ankle. Number 6 you're going to be learning about later on this week. This will be one that I'm going to openly admit to you all. You're not going to very much like it. This is the one that's going to come back into play in this class. That once we get away from it, you're going to say, oh, thank you, Jesus. And then when it comes back into play, you're all going to go, why is it back? The devil is trying to kill me. Number 6 is the amount of substance. The amount of substance. This is the mold. How many of you have ever heard of the mold? And I'm not talking about that little brown creature that's out in your yard or that thing that grows on people's face and you're like, ew. Nobody's heard about the mold before? Fantastic. That means we get to have a good time this week. The mold. Are you ready for the abbreviation of this? This is another one of those moments we go, really? Why? Abbreviation for mold? M-O-L. Why? I have no idea.
So they just left off the E?
Yep, that's it. You got it. That's the abbreviation symbol for the mold.
Why can't they just write the last letter? That's
Yep.
crazy.
That's what I said. Hey, it's all good. Then we got number 7, the last one we're going to talk about. Number 7 is luminous intensity. Luminous intensity. Does that help? I forget how big this list gets. Luminous intensity, the unit for this is candela. Where do you think they got this from?
Mandela?
Nope.
Candle.
What'd you say?
Candle.
A candle. What does a candle do? Gives light. So this is a measure of light being given off, and an abbreviation for it makes sense. It's just CD. But lowercase. If you do capital, that's a compact disc. Doesn't mean that's a joke. Bad thing is I think I almost rolled that ankle, and I messed up over the summer. We're good. Over the summer, my wife asked me to throw away a watermelon. It's been in the fridge for about a week and a half. And when she asked me to do that, I go out in the yard and I'm carrying the watermelon. It's pitch black. You know, we were living on the edge. We was grocery shopping, and exactly at 8 p.m. When we get back home, it's like 11, and I'm sitting there and I'm holding it like a shot put, and I'm walking through my yard. And some AEP truck that's got like the double wheels on the back drove through my yard when a bunch of rain had happened. So they made these big ruts. So I'm just like walking through, and I'm thinking, man, it's gonna be good. I'm gonna go to sleep. I'm gonna wake up in the morning, I'm gonna leave at like 6:30, I'm gonna go on a fishing trip, it'll be a great day. So I'm walking through it, I get about halfway, and my foot goes right in a rut, and I'm gonna roll it. And as I roll it, I'm going down to catch myself, I throw the watermelon up. Did not intend for that, I just wanted to catch myself. So then I catch myself on my knees and on my hands, and the first thought that came to my mind is, God, please tell me I didn't break my ankle, I want to go fishing. And so I'm sitting there and I'm like, oh God, please. And it's like slow-mo. And then I know where I just feel, man, I promise you, you can't make this up. It literally smashes me right on the head. And Mary runs out and says, are you okay? Are you okay? I'm like, I got roll my ankle. I got roll my ankle. So she's like, are you okay? I'm getting my shoes. Just wait, just wait. And I'm just sitting there, I'm praying. I'm like, God, please let me go fishing. Please let me go fishing. And so she comes out there and she's like, are you okay? I'm like, yeah, I think I can go fishing tomorrow. It feels okay. So and she just starts laughing and said, are you serious? That's what you're going to talk about? I said, yeah, it's important to me. I want to go tomorrow. It's going to be a good trip. But you want to hear something really funny? She said, what? I said, touch the top of my head. It's pitch black outside. So she goes, oh, what is that? I said, that watermelon you had me throw out. So we sat there in the middle of the grass at 11:30 at night, just laughing.
I thought you passed out or something.
I do not know why. It was very weird. I've never done it before. I was just walking backward and that ankle just rolled. The funny thing is, if you want it, it'll be on YouTube, so you can edit the clip and take it. Put me on like Teacher Fails or something. Alright, so that right there is the International System of Units. So like to show you like what I'm talking about is all other units are just variations of it that involve it. So like an example is acceleration in physics. Well, let's do velocity first. Velocity is a change in displacement which uses length, which is meter, over a change in time, which is seconds. It's meters per second. Acceleration is meters per second squared. Everything you see in this, everything some way works back to these units. Now, we get to start Here are my two gifts for you. First, here are the prefixes. You need to know from peta to femto. This is your remote activity for tomorrow, which you're getting ready to learn how to do. All right. So, we are going to work on something that is what you will see throughout this class. And if you decide to take physics, you also take physics, by the way. I only got 7 people in that class this year. It's not looking good for next year. Just saying. We are going to talk about something that you're going to use throughout. And especially if you go into a science field, you're going to use it throughout your life. These are the metric conversions. Okay? Now, if there's anything I can say, this is the moment I'm going to take to stand on my soapbox for a moment. Units matter. Units bring identity. If I looked at you and said I was going to give you 1,000, how many of you would want me to give you 1,000? You're waiting to hear what 1,000 I'm going to give you. That's the unit aspect of it. If I say I'm going to give you $1,000, how many of you are going to come up here and say, give it to me? Y'all are being shy and bashful. I know it's day one. Look at y'all. It's so nice of y'all. You're like, I'm going to tell you right now, if Mr. Kennedy said he's giving out $1,000, I'm going to the office. Somebody going to be watching y'all. I'm going to get $1,000. And this $1,000, you're going to take it. If I look at you and told you I was going to give you 1,000 parking tickets, how many of you are going to line up for that? Nobody. That unit brings identity. Which brings me to the aspect of the point that probably makes me one of the meanest and most cruel teachers you'll ever deal with. If you don't give me units, your answer is 100% wrong. You can do the math 100% correct, but if there are no units at the end of your number, you are wrong. And I will stand behind that. I've had kids that have taken quizzes of mine that literally should have got an A, but they didn't put the units on it, and they ended up with C's, D's, F's. Put your units. I will mark it wrong. If I'm in a really good mood, I'll write something stupid down. Like if you tell me 1.23 with no unit, I'll put tooth fairies. Cavities, I don't know. I'll just throw something in there. Okay? So in this, we're going to do these metric conversions. So metric conversions, that's where this comes into play that I gave you. Before we go into the metric conversions, I want you guys to get a feel for where the metric system has come from. We do not use the metric system here in the United States of America. Why? Because we're the U.S. and we like to do it our way. But the metric system is a beautiful thing. It makes converting so easy. How many of you in here know how many ounces are in 1 gallon of milk? It's either you don't know or you're just going to stare at me. And like,
I don't know.
128 ounces. How many quarts?
4.
Honestly, I don't know.
2.
How many pints? I don't know. Why? Because it's a complex system. You got to have it to memory. How many quarts are in a gallon? How many pints are in a quart? I have no idea. The metric system is set up beautifully. It's literally just broken into factors of 10. Why? We use the base unit, and then along with the base unit, we pair a prefix with it, and you got the metric system. So, where did this come from?
What does the French Revolution have to do with the time NASA accidentally crashed a $200 million orbiter into the surface of Mars? Actually, everything. That crash happened due to an error in converting between two measurement systems, U.S. customary units and their SI or metric equivalents. So what's the connection to the French Revolution? Let's explain. For the majority of recorded human history, units like the weight of a grain or the length of a hand weren't exact and varied from place to place. And different regions didn't just use varying measurements, they had completely different number systems as well. By the late Middle Ages, the Hindu-Arabic decimal system mostly replaced Roman numerals and fractions in Europe. But efforts by scholars like John Wilkins to promote standard decimal-based measures were less successful. With 250,000 different units in France alone, any widespread change would require massive disruption. And in 1789, that disruption came. The leaders of the French Revolution didn't just overthrow the monarchy. They sought to completely transform society according to the rational principles of the Enlightenment. When the new government took power, the Academy of Sciences convened to reform the system of measurements. Old standards based on arbitrary authority or local traditions were replaced with mathematical and natural relationships. For example, the meter, from the Greek word for measure, was defined as 1/10,000,000th between the equator and North Pole. And the new metric system was, in the words of the Marquis de Condorcet, for all people, for all time. Standardizing measurements had political advantages for the revolutionaries as well. Nobles could no longer manipulate local units to extract more rent from commoners, while the government could collect taxes more efficiently. And switching to a new Republican calendar with 10-day weeks reduced church power by eliminating Sundays. Adoption of this new system wasn't easy. In fact, it was a bit of a mess. At first, people used new units alongside old ones, and the Republican calendar was eventually abandoned. When Napoleon Bonaparte took power, he allowed small businesses to use traditional measurements, redefined in metric terms. But the metric system remained standard for formal use, and it spread across the continent, along with France's borders. While Napoleon's empire lasted 8 years, its legacy endured far longer. Some European countries reverted to old measurements upon independence. Others realized the value of standardization in an age of international trade. After Portugal and the Netherlands switched to metric voluntarily, other nations followed, with colonial empires spreading the system around the world. As France's main rival, Britain had resisted revolutionary ideas and retained its traditional units. But over the next 2 centuries, the British Empire slowly transitioned, first approving the metric system as an optional alternative before gradually making it official. However, this switch came too late for 13 former colonies that had already gained independence. The United States of America stuck with the English units of its colonial past, and today remains one of only 3 countries which haven't fully embraced the metric system. Despite constant initiatives for metrication, many Americans consider units like feet and pounds more intuitive. And ironically, some regard the once revolutionary metric system as a symbol of global conformity. Nevertheless, the metric system is almost universally used in science and medicine, and it continues to evolve according to its original principles. For a long time, standard units were actually defined by carefully maintained physical prototypes. But thanks to improving technology and precision, these objects with limited access and unreliable longevity are now being replaced with standards based on universal constants, like the speed of light. Consistent measurements are such an integral part of our daily lives that it's hard to appreciate what a major accomplishment for humanity they've been. And just as it arose from a political revolution, the metric system remains crucial for the scientific revolutions to come.
Alright, so there's your history lesson for the week of where this came from. Now, in this, on the board I've drawn our first metric conversion that we are going to do. I'm going to openly look at you and tell you, this is what I would consider a hard one. The reasons as to why, you already start with an exponent and then you have a unit with an exponent. This is area. This makes things more difficult. Now, in this, I want to make sure I'm clear and plain on something. We are looking for something very important here. Here's the golden rule I'm going to give you. This is my method. I will show you the conversion method also, but I'm going to show you my method first because honestly I like my method more. I'm a little biased, but I think you're going to like my method more as well. I really believe you're going to enjoy it more and you're going to prefer it. So in this, step 1 to my method, write the number down in the spot, in the blank. 17.96. Then we are going to put times 10. And this is where my method comes into play. We are looking for the most important part here. This something and other. And other. We are trying to find what something and other is. To do this, I have set up a method for how I like to do it. the first thing I do, I find the difference in the prefixes. So here's the thing. Here's what you're going to need to do. Find your base unit. How do you know it's the base unit? It's the same letters. What's ever in the first and what's ever in what you're converting to. Those letters will match up. Those are your base units. In this case, which one of these are the same?
Meter.
Meter. The M, which stands for meter. Look at that. Y'all are applying something you just learned. Oh, wow. So the meter is our base unit, which tells me the K and the N are my prefixes. So what I'm looking at, I will be looking here at the K, and I will also be looking here at the N. Now, you find the difference between the prefixes. I use that word very, I use it on purpose. There we go. I use it on purpose. Kilo. This is where I said we care about the exponents. What is something another? It is an exponent. If you don't want to put something another, you don't have to, but I'm just saying, I keep calling it something another. So kilo. Look on your prefix chart, find kilo. Go over to the exponents. What is the exponential value for kilo? 10 to the third. So we care about what the exponent is. It's 3. You write what comes first. It's like you're reading left to right. So we write kilo first, it has a 3. We are finding the difference. Since we're finding the difference, you subtract. Then look here at nano. Look on your prefix chart, find nano. What is the exponential value for nano? -9. The negative matters. In my method, keep the negative. So -9. Now, in math, when you subtract a negative, what is it like? You're just adding. So 3 minus -9 is also equal to 3 plus +9, which is 12. So I want to take a moment. I want to spell out the steps that we're going through. I like to do a hard one first to spell out the steps. Then we'll start simplistic and build. First, write the number given down. Please understand, when I'm saying write the number given down, I'm talking you're writing everything but 17.96 times 10, but you leave the exponent blank. You are going to find the exponent. That's what something another is. Step 2. Figure out your prefixes. This also means find your base units. Well, base unit. Step 3, find the difference in the prefixes. All right. That's what we've gotten to here. We have now made it here to step 3. We found the difference in the prefixes. From this point, step 4, we will multiply by exponent on the units. So in this,
She owes you some more, but I'm running out. This is for emergency, I don't know, like somebody doesn't have one.
I got it. I'll throw it at them and say it's for an
Remind
emergency.
me that I need to get some more.
Sweet. Thank you, ma'am.
You're welcome.
So in this, we're going to multiply by the exponent on the units. What's the exponent that's on our units?
12.
On the units.
2.
There's a 2. That's where this is going to come into play. We're going to multiply by that 2. So we take the number you just found, multiply it by 2. What's 12 times 2?
24.
Man, y'all are smart. I'll tell you what, those SAT scores, they going up yet? Woo! We've taken care of almost everything. But, last step. I think it's the last step. Let me make sure. It's been a while since I did these. Boom, 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 boom. Yes. Step 5. Add the exponent you started with. Did we start with an exponent? This is talking in terms of the number. Here, did we start with an exponent? What's the exponent?
3.
So now we're going to add that. So we literally will add 3. 24 plus 3? Woo! Man, y'all good. You have now found what something another is. I know that seems very complex. Promise you it's not that bad. Once you figure that out, you just come in here, it was nanometers squared, and you just write the 27 with the exponent. How y'all feel with that? This is kind of how I like to teach, just to be honest with you. I don't like to give, like, let's be honest. Do you think you would ever read these steps inside of a textbook?
Probably not.
No! I didn't use a big bunch of fancy words, and I didn't draw out this long grammatical sentence. No, I just told you what we're doing. That's how I like to teach. I just like to present it to you as simple as I can, okay? Sometimes it can't come off simple, but I try as best I can. If you got questions, that's where you need to ask. Is there any questions here? I will openly look at you and tell you this is a hard one. All right, let's do an easy one. I'm going to leave the steps up over there. Oh, 4.12. Let's do candelas. Is equal to how many mega candelas? All right, step 1. What do we do?
Write down the number given.
Write down the number you give them. So 4.12 times 10. Leave it blank. No exponent right now because we're trying to find what something another is. So we write that number down. We go to step 2. Figure out your prefixes. This also means your base unit. So in this, What's the same here and there?
Candela.
The candela, the CD. So CD's the same and CD's the same. What does that mean? Do I have a prefix here? No. So look on your prefix chart. You see what says base? It's 10 to the 0. We're still going to use that information. That's why I gave you this one. What's the prefix over here?
Mega.
Mega. So we're looking here at mega. So let's move to step 3, find the difference in the prefixes. Here we said we don't have one. What's the exponential value for the base unit?
0.
0. 0 minus, what's the exponential value for mega?
6.
6. 0 minus 6 is -6. Units matter. Signs matter. Number 4, multiply by exponent on the units. Is there an exponent on the units? So it's understood to be a 1. And what is anything times 1?
Same number.
The same number. So are we going to multiply by anything? No, we're not going to waste time. Step 5, add the exponent you started with. Is there an exponent we started with? Guess what we just did? You just found that something another is. 4.12 times 10 to the -6. I'm going to give you a piece of advice. When you're doing these, a good way to check yourself is looking at your units. It's not 100% effective, but it really helps. What is bigger, a kilometer or a meter?
Kilometer.
A kilometer. Kilometer is what we call wumbo. Do you guys know what wumbo is? You've never heard of wumbo? Wumbology, the study of wumbo. He, she, me, wumbo, wumboing. Oh my goodness.
They have an entire song and band dedicated to that.
That is very nice. Wumbo is big. Mini is small. The kilometer is big. I love I can scan the room and I can tell who got the reference and who did. You got Gage back there. Gage is like, put the W for Wumbo. Pretty much you're looking at the quantity of measurement. Okay, so let's say, I'm going to do it this way. 6.12 kilometers is equal to how many meters? And then we're going to look and say 6.12 meters is equal to how many kilometers. In this, I want to use this for an example. Look at your units. Kilometer and meter. Which one of these are bigger?
Kilometer.
The kilometers. So we're going from kilometers to meters. We've went from a large quantity of measurement to a small quantity of measurement. What that means is our quantity, I need to do a different color, hold on. We're looking at the quantity of measurement. I'm so out of room, man. I need bigger boards. Let's do it here. Quantity of measure. And then we're going to look at the number. So the quantity of measurement has decreased, right? Because we went from a kilometer, which is large, to a meter, which is small. So our quantity of measurement has decreased. The number is kind of what balances out the scale. It does the opposite. So in this case, my number, if the quantity of measurement decreased, the number has to increase. Let's see if it works out. Step 1, write the number down. 6.12 times 10 to something another. We have to find what something another is. Step 2, find your prefixes. I have kilo, and I just have an M, but I have an M in both. So is this milli?
No.
No, what is it? Meter. I can't stress that enough. I will do this to you, and I don't know how many kids will look on here and go, oh, that's milli. No, that's meters. It's by itself. Look what's the same. M and M. If you need to, mark them out so that you can see the prefixes by themselves. So, what's the exponential value here? Remember, we're going to find the difference. So, kilo is what? 3. Find the difference minus, what's the base unit exponential value?
Nothing.
Nothing, 0. You are all correct. 3 minus 0 is 3. So 6.12 times 10 to the third power. Did the number increase? Which is greater, 6.12 or 6.12 times 10 to the third? 6.12 times 10 to the third. This is a way of checking yourself. My quantity of measurement decreased, the number has to increase. Now, look down here. Quantity of measurement. I'm going from meter, which is small, to kilometer, which is large. What did the quantity of measurement do?
Increase.
It increased. Since the quantity of measurement has increased, the number does the opposite. What does the number have to do?
Go down.
Decrease or go down. So in this, let's look. Figure out your prefixes. What's the same in them? What's our base unit? Meters. So we're going to mark these meters out so that you can see it. Do you see there's nothing here that's not marked out now? So that means there's no prefix. That's the base unit. What's the exponential value for the base unit? 0. We're going to subtract. What's the exponential value for kilo? 3. 0 minus 3 is negative 3. I should have wrote my number down first. I apologize. 6.12 times 10 to the negative 3. Which is larger, 6.12 or 6.12 times 10 to the negative 3?
6.12.
6.12. So the number decreased. They will do opposites. Inversely proportional. Everybody good? Okay. Oh, I got to introduce something to you before you get out of this class today. It deals with this. We're not leaving this yet. Okay, this is literally this. We were going to keep working on these until we leave this class today. But I want to show you something. The first problem we did was area. How do you know you're dealing with area? Unit R squared. Third, if it's to the third, it's volume. And then the units are cubed. Here's the thing. There's something very, very interesting. How many of you have ever heard of the liter? How many of you have ever drank out of a 2-liter bottle of pop? Thank you. I'm getting some involvement. I'm getting the T-Rex hands. I love how it is, especially like with the freshmen. You gotta tell them to stick it up there. Gosh, I don't know you. In this, here's how we've got to the liter. So this is the really interesting thing. If we took a box that was 1 centimeter by 1 centimeter by 1 centimeter. In other words, exactly, centimeters cubed. That is equal to a box that has a volume of 1 milliliter. What I'm saying is in this, I'm giving you an identity. This is a trick I will use. This is literally the simplest catch in the world. If you catch it, you will love it. If you don't, you will hate my guts, probably walk out of here and say, I wish Mr. Hall would die. 1 cubic centimeter is equal to 1 milliliter. Yes, I will use this. I will use this in other instances in this class. Remember what I told you at the beginning of this class. Once you learn it, it's fair game. I will use this throughout the class. You need to make sure you remember this. The dead giveaway. If you are ever dealing with a conversion problem, and I have it drawn out like I have, and you see the units going from cubed to no exponent, you hit the brakes and you say, something's up. It's this simple. If I looked at you and I said 178.62 times 10 to the 268 power cubic centimeters is equal to how many milliliters? Easiest conversion problem I will ever give you.
178.62 by 10 to 268.
Exactly. 178.62 times 10 to the 268 power. It's a 1-to-1 ratio. They're equal. That's the equivalent of me saying, I'm going to give you a free problem. You literally just have to copy the number down. This only works for centimeters cubed and milliliters. Okay? Any questions? How are you guys feeling with this? For the love of God, y'all got to open up with me. You got to talk with me and communicate. Life's going to get harder from here. If you're not willing to communicate with me now, it's going to end bad. And I'm not going to do that whole elementary thing.
If you're doing good, give me a thumbs up. If you're like, yeah, I think I'm getting it, give me a thumbs to the side. If you're like, I have no idea, Mr. Hall, give me a thumbs down.
Talk with me. How you guys feeling?
Pretty good.
Okay. What time we got? We're good. Before you get out of here, I want to show you the other method. Now, I will look at you and tell you you can use whichever method you want. This is my method. This method only works for metric conversions. Later on, we're going to be doing mole conversions. When we get into mole conversions, the world changes. Big time. Okay? I'm going to show you how you can always do a conversion and it be correct. This is the method that inspired me to come up with my method, because it literally takes so stinking long, and by the end of it you're like, oh dude, that's up. In this, we're going to start off, let's do something a little simple. Let's do 16.4. I'm not going to do any exponents because literally at this point we'd be using a calculator. So let's do like 16.4, and this will be a good time. Remember me telling you that micro is different than what you see there? Here is what micro looks like. Let's do micropascals. That is micro. It's like a slanted italic U with a really big line at the front of it. That's what micro actually looks like. Do not give me this. If you give me that, that's wrong. If you give me this, that's wrong. If you give me that, as long as it doesn't look like a capital letter like that, I'll give you credit because I'm not going to get on to you for your handwriting. So let's do, just to work this simple and easy, micropascals.
Teachers are getting ready to change classes, so go ahead and allow your